Hi, my name is Michael Fischer, and welcome to this short video summary of our CVPR 2024 paper on NeRF analogies, example-based visual attribute transfer for NeRFs. This is joint work with my collaborators from Meta Reality Labs Research in Seattle and my supervisor Tobias from UCL, and it was completed during my internship last year. A neural radiance field, or NeRF, jointly encodes the geometry and the appearance of a 3D scene. Together, these two quantities make up the scene, but in NeRF-type methods are very hard to edit due to the implicit representation. We here ask the question, how can we transfer this appearance onto a new target geometry? In their 2001 paper, Hertzman et al. Introduced the concept of image analogies. Here we start from an image pair A and A' that share a certain relation, for instance, that A' is a filtered version of A. Now, given a new image B, the task in an image analogy is to infer the same relation for B' such that the analogy relation holds. We can say A' behaves to A as B' behaves to B. In our work, we aim to leverage this idea to enable semantic appearance transfer in 3D. Given a source NeRF, we can think of it as encoding the relationship between geometry A and appearance A'. And now, if we're provided with a new geometry, we'd like to find the target NeRF that contains this new geometry in such a way that the analogy property is satisfied, meaning that it shares the semantically related appearance from the source NeRF. This problem of semantic appearance transfer has been researched in prior work, both in 2D and 3D. In 2D, there are several methods on semantic appearance transfer, such as deep image analogies, VIT splicing, or diffusion features. Unfortunately, they are not multi-view consistent as they work on 2D images. So if we naively lift them to 3D by simply training a NeRF on the individually processed frames, we get floaters and lots of free space density artifacts. In 3D, a popular new research field is appearance transfer based on text prompts, where a text prompt is used to update the source NeRF. However, the prompt embedding is usually a black box, and achieving the exact desired edit can be challenging, as shown in this case, where the NeRF edit does not accurately reflect the prompt. Feature fields, on the other hand, allow multi-view consistent semantic editing by projecting VIT features to 3D, but are limited to simple edits such as scale or color. Our method, in contrast, allows the multi-view consistent and semantically meaningful transfer between the appearance of a source NeRF and an arbitrary 3D target geometry. Our pipeline is divided into three main steps: feature extraction, correspondence matching, and the training of the actual NeRF analogy. Let's look at each of those in a bit more detail. For feature extraction, we render both the source NeRF and the target geometry from different viewpoints, generating a set of corresponding 2D images. For each of these images, we extract dense feature descriptors using a vision transformer, specifically DynoVIT. We use the key features of the attention block in the deepest layer, as these have been shown to best capture the semantic meaning of DynoVIT features. So now every pixel in both the target and the source image is associated with a deep feature descriptor. To find the correspondences between these features, we sample random pixels on the target views and compare their cosine similarity with the source features. For instance, for this roof pixel here, the feature similarity would look like these heat maps, where red means high. We then select the most similar feature as correspondence and look up its RGB values in the source NeRF. We repeat this process many times, as shown here, and so form our NeRF analogy training pairs, where the input is the 3D position of the target together with the normal and the source viewing direction, and the supervision is the appearance of the source at these correspondences. With this training set, we can now train our NeRF analogy. We use the standard NeRF architecture and run a simple, fully supervised training. However, the correspondences we computed earlier can be noisy because DynoVIT is a 2D method that does not have 3D consistency. This results in blurry outputs, which we fix by adding an additional edge loss to the training in order to bring back high-frequency details of the target. This gives us a final NeRF analogy, which combines the source appearance with the target geometry in a multi-view consistent way. We test our method on various object pairs, where the task is always to transfer the appearance from the source onto the target at semantically related locations. We compare against some 2D baselines, which we lift to 3D by training an instant NGP on their 2D outputs. These baselines are not multi-view consistent and show a lot of artifacts and floaters. We also compare against the 3D baseline's NeRF, which compares style transfer with NeRF training, but struggles here due to the non-stationarity of the target images. Our method transfers the appearance in a semantically correct way and is free of artifacts and floaters. We also show results on the real-world datasets from the mid-NeRF 360 scenes, where we replace the excavator with a skid steer and the vase in the garden scene with a different type of flower pot. Finally, we confirm these qualitative findings quantitatively through a user study where our method is preferred by a large majority of users. However, NeRF analogies are not free of limitations. We build on DynoVAT and therefore heavily depend on its prediction quality. It's well known that for the case of specular rotation symmetric objects, the dyno correspondences are inaccurate. Our method currently has no way of knowing this, and here tries to consolidate this by encoding the correspondence noise into the viewing direction, which leads to incorrect view-dependent appearance changes. To sum up, we have introduced NeRF analogies, a method for visual appearance transfer between semantically related parts of two radiance fields. Our method uses dyno features, is multi-view consistent, works on synthetic and real data, and is preferred by a large majority of users. That's it. Thank you for listening, and you can find the code and data on my website and GitHub page.